Quasi-hereditary algebras, lecture 11, modules with standard and costandard filtrations. Let us recall our setup. Let K be an algebraically closed field and A a finite-dimensional K algebra. Let L1, L2 and so on Lk be a fixed order on the set of representatives of isomorphism classes of simple A modules. And we assume that our algebra A is quasi-hereditary for this order. So we have the standard modules delta I, where I is between 1 and k. Delta I is defined as a quotient of pi by the trace in pi of the projective modules pi plus 1, pi plus 2, and so on pk. And we also have the costandard modules nabla I, which are defined as the intersection of the kernels of all homomorphisms from the injective envelope II of Li to the injective modules I plus 1, I plus 2, and so on, all the way up to Ik. And since we assume that A is quasi-hereditary, this means that all projective A modules have a standard filtration and all injective A modules have a costandard filtration. More generally, we have the category F delta of all A modules which have a standard filtration. A standard filtration is a filtration with standard subquotients. And we also have the category F nabla of all A modules which have a costandard filtration. That is a filtration with costandard subquotient. We know that any module M in F delta has well-defined multiplicities of standard modules inside M. So the multiplicity of delta I in M equals the dimension of the home space from M to nabla I. Similarly, for any module N in F nabla, the multiplicity of nabla I in N equals the dimension of the home space from delta I to N. In particular, it is well defined. All the above is a consequence of the property that standard and costandard modules over a quasi-hereditary algebra form homologically orthogonal families. This means that the dimension of the M's extension space over A from delta I to nabla J is equal to 1 if I is equal to J and M is equal to 0, and it is 0 otherwise. More generally, given a module M with standard filtration and a module N with a costandard filtration, for any positive integer M, the M's X space over A from M to N vanishes. Now we can formulate the main result for today's lecture. That's a theorem which is due to various authors, in particular to Rinel, to Auslander and Buchweiz, and Auslander and Drayton. Claim 1. The category F delta coincides with the category of all A modules M, for which the first extension from M to any costandard module vanishes. Also, the category F delta coincides with the category of all A modules M, for which all extensions of positive degree to all costandard modules vanish. Also, F delta coincides with the category of all A modules M, for which the first extension to any module with costandard filtration vanishes. And finally, F delta coincides with the category of all A modules M, for which all extensions of positive degree into all modules with costandard filtration vanish. So here we have various descriptions of the category F delta. And claim 2 of the theorem is a similar statement for F nabla. So F nabla coincides with the category of all A modules N, for which all first extensions from standard modules to N vanish, or for which all extensions of positive degree from standard modules to N vanish, or for which all first extensions from all modules with standard filtration vanish, or for which all extensions of positive degree from all modules with standard filtration vanish. Before we can prove this theorem, let us record some elementary facts. So first of all, we will prove only claim 1, and claim 2 follows directly from claim 1 applied to the opposite algebra of A using the usual vector space duality. We will denote by X the category of all A modules for which first extensions into costandard modules vanish. We will denote by Y the category of all A modules for which all extensions of positive degree into all costandard modules vanish. We will denote by U the category of all A modules for which all first extensions into modules with costandard filtration vanish. And finally by V the category of all A modules for which all extensions of positive degree into all modules with costandard filtration vanish. Directly from the definition, we have the following diagram of inclusions. Of course, Y is included into X, so if all extensions of all degrees vanish, then all first extensions vanish. Similarly, U is included into X. If all first extensions into modules with costandard filtration vanish, then all first extensions into costandard modules vanish. And similarly, V is a subcategory of Y, and V is a subcategory of U. And as we mentioned on the previous slide, we know that F delta is a subcategory of V. So if you have a module with a delta filtration, then all extensions of positive degree from this module into all modules with costandard filtration vanish. So we have this obvious diagram of inclusions, and so to prove claim 1, we just need to prove that X is a subcategory of F delta. So that's the only thing which we need to prove. X is a subcategory of F delta. We will prove this claim by induction on the number of simple A modules. We denoted that by K. The basis of the induction is when K is equal to 1. In this case, A is a semi-simple algebra, so all extensions vanish, which means that F delta is just A mod, and so the claim is obvious. So let us prove the induction step. We assume that K is greater than 1. Let I be the ideal of A, which is given by the trace of the projective module Pk in the regular module A. Denote by B the quotient of A modulo I. Then B is a quasi-hereditary algebra. M from our previous lectures we know that for any B modules M and N, the extension space of degree M from M to N over B is isomorphic to the extension space of degree M from M to N over A. So the inclusion of B mod into A mod is a homological inclusion, so all extensions are preserved. Okay, let us now take M, a module in our category X. So we know that all first extensions from M into costandard modules vanish. We need to prove that M has a standard filtration. That's our aim. Consider the trace in M of the projective module Pk. We can alternatively describe this trace as the submodule of M given by multiplying M with our ideal I. And so we have directly from the definition the short exact sequence that this trace embeds into M, and we denote by coker the corresponding cokernel. Then, from the definition of the trace, our coker doesn't have any composition subquotients which are isomorphic to Lk. So the multiplicity of Lk in coker is 0. Now let us apply to this short exact sequence the functor hom over A blank nabla I, where I is smaller than K. Then we have a long exact sequence in homology, and in that long exact sequence we have the following part. So we have hom from our trace to nabla I goes to the first x from cokernel to nabla I, and then the map goes to the first x from M to nabla I. the first x from M to nabla I vanishes because M is an x. That's our assumption. In our trace, any top constituent of our trace of pk in M is isomorphic to Lk. And we know that there are no Lks in nabla I. So this home space on the left is 0. So the left term is 0 and the right term is 0 and the sequence is exact. So this means that the middle term is also 0. In other words, the cokernel has the property that for any I smaller than k, the first x over a from the cokernel to delta I vanishes. But cokernel is a B module, and the first x over a is the same as the first x over b. So which means that our cokernel is in the category x for b. And so we can apply the inductive assumption and conclude that our cokernel has a delta filtration as a B module. But then of course the same filtration is a delta filtration as an A module. So we just proved that our cokernel belongs to F delta. It remains to show that our trace also belongs to F delta. For this, we look into a different part of our long exact sequence from the previous slide. So we have the first x over a from M to nabla goes into the first x over a from the trace to nabla, and this goes into the second x over a from the cokernel to nabla. So the left-hand side is 0 because M belongs to x, and the right-hand side is 0 because we just proved that cokernel has a delta filtration, and so all x into nabla vanish. But then this means, due to the exactness of the sequence, that the middle term is also 0. So we just proved that the first x from our trace into any nabla I where I is smaller than k is 0. Okay, now let us look at the module trace from pk into M a little bit closer. By construction, this module is a quotient of a certain number of copies of pk. Let's denote this number of copies m, and we can compute this m as the multiplicity of lk in our trace, and also as a multiplicity of lk in the original module m. Now we consider the short exact sequence, so we have this projection from pk plus and so on m times onto the trace in M of pk, and it has some kernel. Let's denote it by ker. By construction, we have that our kernel doesn't have any composition subquotient which is isomorphic to Lk. In other words, any non-trivial composition subquotients of ker are of the form Li, where I is smaller than k. Because all appearances of Lk, they appear in the top of pk, and there are as many of them as the multiplicity of Lk into the trace in M of pk. Great. So now we apply to the short exact sequence the same functor as before, hom over a blank nabla I, where I is smaller than k. Again, we get a long exact sequence, and in that long exact sequence we have the following part. So we have hom over a from pk m times into nabla I. This goes into the hom from ker to nabla I, and this goes into the x1 from our trace to nabla I. Any top constituent of pk is lk, and there are no lk's in nabla I, which means that the left term here is 0. Above, here, we established that the right term is also 0, which means that the middle term is 0. So there are no homs from ker to any nabla i's where I is smaller than k. If ker were non-zero, then the top of ker would contain some simple module Li, where I is smaller than k. Because ker doesn't have any Lk's, we knew that. But then we have a non-zero map from the kernel, which projects onto this Li, and this embeds into nabla I. Therefore, in this case, the home space from ker to the corresponding nabla I would be non-zero, but we have proved that it is 0. So it follows that the kernel is actually the zero module. And this means that our trace of pk in M is isomorphic to the direct sum of a number of copies of pk, so it's projective, and so it has a delta filtration. And in particular, it follows that our original module has a delta filtration, and this completes the proof of our main result. Now let us look at some examples. Example 1. Consider an algebra A with the following property. If x1 from Li to Lj is non-zero, then I is smaller than j. So this is one of the types of directed algebras which we looked at in the previous lecture. So we know that this A is quasi-hereditary with simple standard modules. Therefore, f delta is just A mod, because any A module has a filtration by simple modules. At the same time, the costandard A modules are injective, and therefore f nabla is just the category of all injective A modules. And of course, injective A modules are exactly those A modules for which the first x from any simple vanishes. And also, dually we can say that any A module has the property that the first x into an injective module vanishes. Example 2. Let us now consider the directed algebras in the opposite direction. So let A be such that the existence of a first x from Li to Lj implies that I is greater than j. Then A is quasi-hereditary with projective standard modules, and therefore f delta is just the category of projective A modules. At the same time, the costandard A modules are simple, and so f nabla is the whole category A mod. And again, A mod coincides with the category of all modules for which the first x from any projective vanishes, and the category of projective modules coincides with the category of all modules for which all first x into all simple modules vanish. So this is checking of our theorem on some easy examples. Here is the third example where one can compute things explicitly because it has finite representation type. Consider the path algebra of the following quiver. We have three vertices, 1, 2, and 3, an arrow from 3 to 1, and an arrow from 1 to 2. So this is a representation finite algebra. It has 6 indecomposable objects. The object L3, which is also the injective object I3, which is concentrated at the vertex 3, it's one-dimensional there, 0 everywhere else, and all arrows are the zero maps. We have the simple module L1, which is one-dimensional at the vertex 1, zero-dimensional everywhere else, and all arrows are 0. And we have the simple module L2, which is the same as the projective P2. It is one-dimensional at the vertex 2, zero-dimensional everywhere else, and all arrows are 0. Next, we have the injective module I1, which is one-dimensional at the vertices 3 and 1, with the identity map between them, and then we have 0 everywhere else. We have P1, which is one-dimensional at the vertices 1 and 2, with the identity map between them, and 0 everywhere else. And then we have P3, which is the same as I2, and this is one-dimensional everywhere, and all arrows are the identity maps. Okay, the algebra A is hereditary because there are no relations, and so it is quasi-hereditary for any order. Let us compute the standard and the costandard objects for our order which we chose. So the usual order 1 is smaller than 2, and 2 is smaller than 3. But note that 1 in our case is a middle vertex, 3 is a source, and 2 is a sink. Okay, so we have the following standard modules. Of course, delta 1 is L1 because 1 is the smallest vertex. Delta 2 is L2 because the projective is simple. But delta 3 is actually P3. That's the usual sink. So delta 1 is L1, delta 2 is L2, delta 3 is P3. How about costandard modules? Okay, nabla 1 is of course L1, nabla 2 is P1, and nabla 3 is L3 because I3 is simple. So we have nabla 1 is L1, nabla 2 is P1, and nabla 3 is L3. Now we can describe explicitly all indecomposable objects in F delta. So we have the standard modules L1, L2, and P3, and also P1, which is an extension of L1 and L2. And we can describe indecomposable objects in F nabla. So these are the costandard modules L1, P1, and L3, and also the injective module I1, which is clearly in F nabla because it's injective, and the module P3, which is also I2. Note that L3 is not in F delta, and one can check that the first x from L3 to L1 is non-zero. That's because we have an arrow from 3 to 1. And also I1 is not in F delta, and here one needs to compute that the first x from I1 to P1, P1 is in F nabla, is non-zero. And also L2 is not in F nabla because the first x from L1 to L2 is non-zero. There is an arrow from 1 to 2. So this is an explicit check that the category F delta is exactly the category of all modules for which the first text into F nabla vanishes, and vice versa. And an interesting observation for the next lecture, if we look at the intersection of F delta with F nabla, we get 3 indecomposable modules, L1, P1, and P3. So the number of modules in this intersection is the same as the number of simple modules. This will be one of the main points for the next lecture. Okay, some extra problems and questions. Problem question 1. Prove the second part of the main theorem with all details. Problem question 2. Let A be a quasi-hereditary algebra with simple standard modules. Prove that A is directed. Problem question 3. Let A be a quasi-hereditary algebra with projective standard modules. Prove that A is directed. Problem question 4. In example 3, check the x vanishing between modules in F delta and F nabla by explicit computation. And problem question 5. Compute an analog of example 3 for the path algebra A of the following quiver. We have 3 vertices, 1, 2, and 3, and an arrow from 2 to 3, and an arrow from 3 to 1. Thank you very much, and see you next time.